So I thought I'd tell a little bit of a lunchtime story. So just to get us warmed up here. So the AI Institute, I'm really going to talk a little bit about almost a philosophical stance we want to think about in what we want to do at this institute. So it's really going to be framed towards that in terms of a storyline that I think everybody here will resonate with. So I think this word is what I wanted to bring into the title. We're at a point now where we can really start thinking about taking the tools of machine learning and really improving our pace of engineering design and engineering progress, as well as scientific discovery. And I think that's a true statement for almost any field you go to. This is just an amazing set of tools we have available today that we can exploit. So I want to start us here because I want to contextualize actually a lot of the issues that we think about with engineering and science discovery that are alive today. But I want to talk about them in terms of they've always been around with us in much different ways. So what you're looking at here is the night sky taken over quite a few months. And here is the retrograde motion of the planet Mars. And that, I believe, is Saturn. Okay. So before cell phones, before your laptop, before electricity even, when it got dark out, you went outside and you beheld the heavens. It was kind of in a simpler time, and it must have been wonderful to be able to see the night sky. And for a long time, I think this is, in my view, this is the first grand challenge science problem, is what dictates the motion, this retrograde motion we saw of the planet. So fascinating was this motion that, right, they gave these names of Greek and Roman gods, okay? And so people really wanted to try to understand that motion and that physics. Of course, they didn't know about gravity at this time. This would be to be discovered. Now, the reason I bring this up is because I want to start thinking about sort of scientific discovery starting from this point. And really one of the big pieces that first came was out of 2nd century Alexandria, Egypt. So Claudius Ptolemy, of course, we didn't have a picture of him, so this is some made up picture of him. He was working in Alexandria, Egypt, and he came up with the first theoretical construct for predicting the motions of the planets, okay? Fascinating story about the pen and the sword. We always say the pen is mightier than the sword, and this is the most, Alexandria, Egypt is probably historically the best representation of the power of the pen and the sword. Alexandria was set up by Alexander the Great, who conquered, who swept through all of Greece, through Persia, through Egypt, and Hellenized the world, had a huge impact culturally on the world. But one of the things that we often miss in that is who was Alexander's teacher? Aristotle. And when Alexander came to Egypt, the Egyptians were not open source people. Their knowledge base was for a small group of elite intellectuals. It was not widely disseminated. When Alexander came through there, he grabbed all that knowledge, brought it up here to Alexandria, where the library was founded. Guess who had access to that knowledge? Aristotle. And you see a big departure after this from Socrates to Plato to Aristotle. And now Aristotle departs into a scientific agenda. And I think largely, and others have speculated largely, because of access to the Egyptian scientific thought that had been culminating for thousands of years. And so this actually changes the world. Claudius Ptolemy is there. This becomes an intellectual hub. You have Euclid who comes to study there. Many great things are happening there. And this first theory comes out of this, which is the doctrine of the perfect circle. And the way that, and there's all these beautiful Renaissance paintings about sort of this idea that the planetary motions were orbits of circles on smaller circles, each with different frequencies. One way to think about it, if you're into signal processing, this is the first version of a Fourier transform. That's how you represent the motions of the planets, okay? And so this doctrine holds for a long time. This is a pretty big advancement because the theory actually works quite well. And so this is 150. And it took a long time for this theory to fall. So let's talk about this process, because in some sense, this process is what almost all of our fields will go through, is this evaluation and as data is collected, an upgrade of theory and of advancement. And so here are the next set of advancements. So this is the early 1600s, and I have three pictures here: Tycho Brahe, Johannes Kepler, Galileo Galilei. Okay, so first of all, I think we could all agree, Mario and Andy were here as our astronomers, and I think we would all agree that we would take them a lot more seriously if they had some really great facial hair like this. So it's not too late, Andy. Really nice beard and mustache. Oh, it'd be fantastic. They're both clean shaven. How do you guys survive over there in astronomy? All right. Well, here's the thing about Tycho. Tycho collected some of the best astronomical data to date, an order of magnitude better than anybody had done previously. Tycho was also not an open source person. And in fact, Tycho guarded that data very carefully. And it wasn't until his death that Kepler was able to acquire it. But it wasn't that easy either, because Tycho Brahe's estate did not want to give that data to Kepler. The interesting thing is Kepler was the ideal person to have the data because he was the person who had the mathematical expertise to actually do the analysis of the data. And 11 years after having access to the data, he publishes his Tableau Nouveau, which basically starts to posit some of the things we know, like Kepler's laws, planetary motions on ellipses, okay? So we look at this. You have about a 1,500-year gap in this scientific discovery process. Once you get this data that finally gets open sourced, sort of, right? Very difficult to get the data. It took another 11 years. Now it's interesting, what if you had put it in an Excel file? And what if Kepler has a Python Jupyter notebook? Could this all have been done in an afternoon, right? This is amazing to think about hand calculations to do this progression of science. Galileo is here too, because he also was really pushing and advocating this idea of the heliocentric universe. He was the first observer with his telescope of actually seeing this dynamics by looking at the Jupiter and its moons, right? So all the groundwork is laid to make a very big advancement in science. And the first advancement that comes after this millennia and a half is that maybe we should switch coordinate systems. We're using the wrong variables. And this is sort of this picture here. So the reason we see the retrograde motion is because both the Earth and Mars are going around the sun. And that was sort of the explanation, is to make a coordinate transformation to sort of move the science forward. With this new coordinate system, there's a little bit cut off here, but 1687 Principia is published. So less than a century, it's this coordinate system that allows Newton in his construction of calculus to come up with this idea of F equals ma. And so you needed both the coordinate system, and now you have a governing set of equation to talk about this evolution of the planets. And of course, we kept collecting data and kept collecting data. Late 1800s, that F equals ma model was not matching up with the data perfectly. And this is improved data is what actually allowed Albert Einstein to propose theory of general relativity. So this is a fantastic conceptual piece from people who did not want to share their data to open sourcing it to progression of scientific thought. And there's two principles I want to try to think about here. Is there was two models that were very successful here. One is this model by Ptolemy, which actually was quite successful. And I'm going to start now bringing it into the modern context, which is I want to take measurements. I want to learn a coordinate system and a representation of that dynamics that I can use in that coordinate system. So I'm not just learning dynamics or learning a model. I'm learning the pairing, and that seems to be a hallmark feature of a lot of our scientific discoveries, get these both. So here in the Ptolemaic model, you take this night sky observation. So this is like a 2D picture. You would run it through this encoder to learn a representation like this, which was circles on circles. That's one model. A second model is different. Learn a coordinate system like this, and in that coordinate system, learn a governing equation. So both were quite successful in making predictions. So here's the question. When we rank everything, right? I knew that we had taken a wrong turn when I showed up at, like QFC when I was many years ago, and they had Seattle Magazine was ranking grade schools, right? It's one thing to rank a college, but when you're ranking grade schools, right? This is that's a little too far. So we like to rank everything. Well, in these rankings of scientists, Newton's always 1-2, along with Einstein. Kepler doesn't usually make the top 10, maybe 10 to 20. Why is that? Because in fact, his Newton's F equals ma, which produces elliptic solutions, already were there from Kepler. So here's the big thing that I would like to emphasize with this. And this actually goes to Ali's comments today. When you go out to the real world, F equals ma by construction is in some sense an extrapolatory engine. This is an interpolation, right? It's a fit to the data. What can you do with extrapolation? Well, here's what we did. 1969, we put somebody on the moon, right? Somebody imagined, well, if I know this force, what would it take to launch a rocket from the Earth, put it in orbit, bring it back? I've never seen data like this, not even close to this. I fundamentally, if I want to do that operation, I have to walk so far outside of my observation. And this is the power of a governing equation. This is why we study physics, is once you have that kind of base model, what you do with it is you try to walk as far outside of that as you can and see if I can build a new technology. And then maybe a different parameter regime than I've measured. And so that legacy is really important. And I think in some sense, here are two versions of what we think about today of autonomy, right? These are grand challenges, problems for us today. One is robotics. Here's a self-driving car. This is quite amazing, right? That's a really athletic robot. I would, at my age now, I'd probably break myself trying to do anything like this. And so these are kind of where we're working, and many of us here in the room are working on things like this. And I would say that these inherit two different legacies. This is, in fact, inheriting the legacy of Kepler. And this is very crude. There's a lot of nuance to this, so if you'll just let me skip through this and say this. But this is really largely physics-based. So that robot has physics models, it has F equals ma knowledge. It moves in its world by knowing what angular momentum is, by knowing what I have to keep its balance. Where this is a car, and it's basically a bank of sensors with labeled data, right? It doesn't have to know F equals ma. It has to have some rules, it has to know where the other objects are, and the rules around those objects, okay? So it's not taking into account physics necessarily, okay? Now there's a big difference between these two. If you leave a car, and if, a car is inherently sort of a very stable object. It doesn't fall over. It doesn't, like when you hit a curb, it falls on its side. Whereas the robot, just keeping it upright and moving and not falling over is a challenging task. So, in some sense, maybe this is why you can get away without having those physics models, because the car's not just going to fall over on you. In fact, you could put 16-year-olds in there and 80-year-olds in there. And for the most part, we do fine with that. We're a little more scared, but there you are, okay? Where I want to spend time is up here. And this is where our AI Institute is. We want to start thinking about how do we start building out models that, in fact, underneath it, we're thinking about systems who have some kind of physics process or biophysics process underneath driving what we observe, okay? So it's not to make a judgment statement, because success can come in so many forms in both of these paradigms. So here's the mathematical framework I think about for us in this institute, which is ultimately there's a dynamic system underneath it. I am looking at a system. It could be a computational neuroscience system. So I'm looking at brain activity. It could be additive manufacturing process, right? So there's some physics process, and I don't necessarily know what the right governing equations are, okay? But I do have measurements of the system. And I think here's where the inversion and the stars of the show are. So the star of the entire show for us in this generation is sensor technologies. That drives the whole data science revolution. What we can do with sensors now is unbelievable. In fact, one of the most exciting sensors that I think it's transform the world is what Mario talked about, 2023, when we start getting pictures back from this new telescope. I think that's gonna be such a fun moment in human history. But it's more than that. Have you seen what people can do in computational neuroscience? What they can measure now in brain activity? While a mouse is doing all these things, you're recording from thousands of neurons simultaneously. So it used to be we'd do a lot of work here with a few measurements, and now we say, I've got so much here, I want you to build me a good model. I want to understand the governing equations and how they're parametrized. And that's kind of I think the paradigm shift for us today. Okay, so this here, just taking measurements and trying to infer governing equations, even a measurement model to a state space. I don't even know what the right variable is. So I need to figure out what the right variables, the governing equations, the ill-posed problems. And so often what we do with these ill-posed problems in machine learning, we regularize them, we impose some constraints. And so really what we're after is explainable, interpretable AI. And that means different things to different people, but let me tell you what it means to me and for us sort of sitting on the AI Institute of Dynamic Systems, which is these ideas of interpretability and parsimony go way back to William of Ockham. He was in 1200s in Oxford. And this was when the revival of Aristotelian logic was coming into Oxford. And they started making some really amazing constructs about logic. And Ockham was very much of the opinion, said, look, make nominal models. Don't put all this extraneous things on things. What is the sparsest, most representative model possible? And that's what we should be doing. So these ideas go back a long way. And that's exactly what we want to be doing here is I want to impose physics models that are as minimal as possible, that has all the right characteristics of the dynamics and it fits that data. I mean, this concept, and there's so many people in between, but Pareto is another person. So we often talk about Pareto front, Pareto optimal. So that's the reason I put Pareto here. And so for us, for physics, this is the ultimate regularization. I want the smallest number of terms and the smallest number of dimensions so that I can represent that physics in a good way. And so that's, doesn't have to be your judgment about what you want, but for us, that's what we want, because we think that if we can get this, then we can explain what we're going to see out of our systems. The other thing I want to highlight is that we all studied a lot. Everybody in this room showed up here and probably has some fancy degrees and lots of education. And so we know a lot of physics. So how do we bring that to the table too? We don't just want to say to a machine learning model, I know nothing, go find it for me. I actually know a lot of physics, and so do you. So how do we bring that to the table? So instead of just discovering engineering and physics principles from scratch, you might know some things that are true. I know that I have to have conservation of mass and conservation of energy in the system, or whatever it happens to be. So you know there are some things that are true, and all you really need to do is find some missing physics. And so that's kind of a big emphasis for us as well. And where does this play out? Well, it plays out in things like the digital twin revolution that we anticipate may come. But the digital twin's a lot harder than you think, because here's your CAD-based model, here's the real thing. You try to match these, they look the right, but if you're doing precision manufacturing, they're off. And this is a platonic model, it's perfect. And what you really need to do is take into account, well, there's frictional forces here in the joints and they change over time. And if you oil it, it's different. So I need to take the data from here and help build a better model over there. Even though I know most of the physics, how do I do it better? So that's kind of the basic ideas. And this is what we're going after. And, you know, it's one aspect of overall AI that's going to come towards physics and engineering. We want everything open source, right? Code, data. There is no Tycho Brahe in our institute that's going to say, I got this data and I'm going to keep it. And when I die, my family's going to try to not let you have it either, right? That's what we don't want. And Kepler, instead of only Kepler could pull off the calculation after 11 years, here's the code to pull it off. And you can verify. These are the kind of things we want to go after. We want to accelerate that process for all of us to do the kind of problems we want to do. Thanks.